We are in section 3.5 CalcAB, no, 3.4. We're working up to 3.5. 3.5 is a grand old, let's put it all together. I waited to start the recording until now, or I should say I waited to give some of these announcements until now. So you guys are writing these notes. Steps for analyzing concavity. It's not a forever card, but it is a reference you can use. Have your notes open to this section when you guys are doing 3.4 homework. My advice over the weekend was to go find as many derivatives as possible to work ahead. Yeah. Like the numbers, like even if you looked at the homework sheet, it looks shorter, but you have to find first and second derivatives. It just takes time.
Repeat the first one wrong.
Yeah, right? Which is why, like, have a Wolfram Alpha, have the back of the book or a Cal Chat open if it's an odd to check the derivative before you move on. You can't do it on a test, but you can't do it on homework.
So obviously you can find the first derivative, and that's fine on Wolfram Alpha, but can you like go directly to the second derivative, or do you have to derive first?
You can try typing in, find the second derivative out. I'm pretty sure they'd be able to do it. I'm not sure if they would show you the first, which is something that you would need to check too, but yeah, that's a good idea. I think you could type in find the second derivative. There's not really a good notation way of putting that though, so I would just say find the second derivative of and then put a parenthesis in the function. Try that. Worst comes to worst, just say derive and then put it in. So on the homework tonight, do the best you can with derivatives, but I don't mind you going and using a crutch. Mrs. Rainier gave a devotion today. She's like, lead with a limp. None of us are perfect, and so to portray that defies the gospel, defies reality, breeds distrust. So in your homework tonight, I know this is a weird application, but in your homework tonight, it's okay to work with a limp, to be like, I'm not totally sure on this derivative, I wouldn't bet my life on it. Don't want to do all the work if it's wrong. Just go check your derivatives first. And then keep going. As far as the calendar goes, we are pushing forward to a test on Friday. For kiddos that are gone, I did remind them of turning in their corrections today. That extra credit quiz to replace problems on your chapter 2B test is tomorrow right at the beginning of class. We're only going to take about the first half of class, so about 20 minutes on it, 15 to 20. So it's not going to be a lot of time, but you're going to do the best you can. From your corrections, even if you're like, wait, I didn't miss any points on the inverse derivative question, well, then, or questions, you can always skip that one on the quiz. If worst comes to worst, go to the ones where you know you missed a lot of points. From your corrections, that should kind of be jumping out at you, like that related rates one. I need to go do that one first. Because there's going to be a long answer related rates question on there. So, for you guys to think of for the quiz tomorrow, you don't have to agonize over every single question. If some of them are your big weak points, spend the time there, and then with any extra time, see if you can get the other ones right. But everyone is taking it. That way I can get you some points back while the corrections are fresh in your mind. But then, on your calendar, right now I have 3-4 finishing today and starting 3-5. I don't know if we'll start 3-5. I have tomorrow as finishing 3-5, and then I have 2 days for review. So I have an AP practice day Wednesday and a review Thursday. We might have to go into Wednesday with 3-5, but that's okay. I made 2 days for review. So if we need to go into Wednesday for section 3-5, we can. So if you guys look at the calendar, this homework is due tomorrow. 3-5 is due Wednesday or Thursday, depending on how we do it. Test is still coming Friday, and I think we should be able to do it. Okay? So excellent job. I'm going to jump on in just a second when you guys get this written down.
If you get 3.5 due Wednesday, could you ever review that Thursday?
Yeah. Like if we can bust out 3-5 tomorrow, theoretically we can have like AP practice / workday Wednesday and then like reviewing all together Thursday, which we have to do. Because that way we can do like our group stuff and look at this time. Back here I'm doing a derivative, just getting ready for an example that's coming today so that you guys don't have to spend all the time doing it. In case you're wondering. A few people are still taking notes. If you guys get to the end of the notes, you can go ahead. You can go ahead to the example. Find the first and second derivative. It should be easy, right? It's a power rule. Go to the example, first, second derivative, and then start looking at the steps and say, okay. Step number 1, domain, all real numbers, no big deal. Step number 2, find the second derivative. Okay, find the first, then find the second. I think I have that derivative ready. Oh, well, that's the first derivative. Okay. Remember for the first derivative test we were finding crits, right? Okay. We were finding domain and we were finding crits. That was for the increasing, decreasing test, I should say. Also known as, or also for relative extrema when we were using the first derivative. So for increasing, decreasing, and for relative mins and maxes, using a sign chart, using the increasing, decreasing changes, we would do domain and pips. Domain and crits. However, when we're talking about concavity or relative mins and maxes with the second derivative, which you don't know quite yet, we're going to need to think about domain and pips. What's the difference with pips? What do you guys see over here that changed? Second derivative. We're still doing zeros and we're still doing DNEs. We're still looking at the top and we're still looking at the bottom if there is one. We're still setting the top equal to 0, or the whole function equal to 0, or the bottom equal to 0. If there is one. If there is a denominator. We're still trying to find the zeros and the DNEs, but of the second derivative now. Not the first derivative, of the second derivative. So, you guys were supposed to find derivatives. What did you find for f prime? And we should know by now that it's always good when we look at a function to check whether or not we can factor, right? So what happens when we factor f prime?
Oh, don't you need f double prime?
Ooh, good. Because why can't we stop at f prime?
It's CalcAB.
It's concavity. It's not increasing, decreasing. So we're going to go one more time. So f double prime is 36x squared minus 24x. You guys agree? Okay, cool. So we found the first derivative, found the second derivative. Couldn't stop at f prime. We're doing concavity now. Second derivative. Now, let's factor. So first derivative power rule, second derivative power rule. When we factor, what comes out? 12x? Good. And we end up with 3x minus 1? Ah, good. My math is a little rusty this morning. 3x minus 2. So, over here, domain, got it. Crits, no, we're doing concavity. We need pips. Pips stand for possible inflection points. We have a forever card in just a second, but basically, pitchfork, 0's DNE of the second derivative. And otherwise, we just follow the same, now that we have the second derivative, we follow the same steps as increasing, decreasing. So what are the zeros of the second derivative?
0 and 2/3.
Good, so that each one equal to 0. And we end up with 0 and 2/3. Kiddos, do you see a sign chart as step 3?
Yeah.
Cool. But instead of putting crits in for concavity, we're putting pips in. So we're going to go ahead and domain, all real numbers, so forever left, forever right. That's why the arrows are headed both ways. Let's throw in 0 and let's throw in 2/3. Ugh. To the left of 0 is easy. Let's check f, double prime of -1. Because if we're doing a sign chart of the second derivative, now we're thinking sine of f double prime. We could plug in behavior of f prime, the increasing, decreasing of f prime, but that's not what they're asking about. They're asking about concavity of f, so we can go straight to, if you want, the concavity of f. The sine of f double prime tells me about the concavity of f. We're going to jump over the behavior of f prime because they're not asking for it, so we're like, okay, fine, no big deal. So we can plug in -1. Up here is easy. We can plug in 1. Bummer, guys. What's something in between 0 and 2/3?
1/2.
Oh, we could do 1/2. Does that sound easier than 1/3? Okay, let's do 1/2. If you guys haven't figured by now, it's very, very, very nice to plug into the nice factored form. So if you plug in a -1, let's see, that's a negative, right? 12 times negative. That's a negative. Plugging in -1, negative minus, that's still negative. A negative times a negative is a, which means f is concave up on that interval. Now I don't know whether it's the decreasing part of concave up or the increasing part of concave up. I'd have to do a sign chart of the first derivative to figure that out.
Oh, snap.
But I do know it's concave up. I do know it's concave up. If you think about it, if we're trying to graph a function, we want to know exactly which part of concave up it is. And so then we might do both sign charts in section 3.5 in trying to get graphs. Plugging in 1/2, that's a positive, right? Okay, how about here? 3/2 minus 2? 1.5 minus 2? That's negative. Positive times a negative?
Negative.
Don't know which branch of concave down, but that's okay, something concave down. And then plugging in 1, I think that's a positive times a positive. You guys agree? So then my final solution, or my final analysis would say that f is concave up on the intervals. You're welcome. Let's see, -infinity to 0. Remember, keep it open again. I'm splitting up with pips, which I forgot to fill in. Those are in-betweens of concavity. They're zeros or DNEs. So the second derivative doesn't have a sign, so I can't say there's a concavity at those points. So keep it open. But I also have 2/3 to infinity, yeah? What's my concave down interval?
0 to g-thirds.
Got it. There's the graph. This section, it's next section that says get the whole graph. This section doesn't say get the whole graph, but guys, do you see how this graph does go concave up for a while? And then concave down for a little bit? And then concave up? Points of inflection would be here at 0 and somewhere in between. Here's where it gets tricky. Check it. The concave up, do you see how it's part of a smile? Okay, it's the decreasing portion of a concave up. Is this super obviously concave down? Not really. But it does go concave down for just a little portion, but then there's another point, and that point's at 2/3, another portion where it then changes to be concave up. So, these possible inflection points, wait a minute, what makes them actual inflection points? Well, let's go ahead and get that down. Inflection points are places or points where concavity changes. By definition, a point of inflection is a point at which concavity changes. How can they occur? Well, there's a few different ways. We could use the graph that we just kind of did. Like, okay, they occur there. It occurs there. My phone's not on, sorry. I didn't turn this on sleep mode, so it doesn't die. What I want to show you guys is points of inflection. All these points that I just sketched, these are all points of inflection, but look at the slopes of the tangent line. What's the slope of the tangent line, f prime, of this first one? Yeah, f prime equals 0. So this would be a crit, right? F prime equals 0, that would be a crit. How about this one? What's the slope of this one? F prime is DNE. F prime does not exist, so it's also a crit, yeah? Oh, so critical numbers are also possible inflection points, but wait. For the graph we just did at 2/3, there was an inflection point, but what's so special about this slope? F prime is negative, it's not 0, it's not DNE, it's not a crit, which is why we don't look at the first derivative for our inflection points. We have to look at our second derivative for our inflection points. First of all, graphs have to have concavity. They can't be linear and have points of inflection. Linear has no concavity, has no curvature. We have to watch out for linear if we were just doing F prime, but we also have to look out for these weird ones where F prime is nothing special. It's just some random negative or some random positive. We gotta look at the second derivative. We can't just stick with the crits because the crits are not the only possible inflection points. So, possible inflection points. Find the second derivative. Do your pitchfork. Look out for your zeros, which is when the top equals 0. Look out for your DNEs, which is when the bottom equals 0. You won't always have both. Sometimes you will. But you're looking for when f of c exists. Can't be a domain problem. That's why we always do domain first. F of c has to exist, and the second derivative is either 0 or DNE. Those are pips. Those are pips. Possible inflection points. So question, what makes them pips? Inflection points. Pips are possible, ips are actual. How do you go from a possible to an actual? You gotta look at a sign chart. Just like relative extrema are critical numbers where the sign changes, mins and maxes depending on how the signs change of the first derivative. Inflection points are pips where the sign changes. So when the first derivative changes signs, f has relative extrema, as long as the function exists. Where the second derivative changes signs, the original function has points of inflection, as long as the original exists. Yes, I'm zooming out. Yes, I'm going to go get a yellow box. Uh-oh. I want a little more space, though. There we go. It's not the entire page. P.S. What are you supposed to be keeping updated? If I were you, I'd have them fully updated by, well, let's say by Wednesday, because that's when we're hopefully starting to review, so you can have your forever cards out and be using them. Remember, for the test on Friday, since we're going full steam ahead, I'm not making you have them all memorized, but you need to know how to use them. So get them in your forever cards. You can be using them on homework. You can be using them in class, okay? This is forever number, I think, 26. Does anybody double check that?
Yeah, I think so.
To that end, I will try to get it updated. Oh, I think I have no free period today. I'll try to get it updated by tomorrow with all the ones from chapter 3. Okay. So with that, kiddos, what if you were ever faced with a question? Identify any points of inflection. Now, you guys can go ahead and get that example down. I'm going to freeze the screen really quickly because I did find a first derivative on the backboard. But to be honest, I try not to put on any sort of facade that I have things all figured out or work together or that I'm perfect in any way, shape, or form. So even though I found a derivative on the back, I'm totally going to go double check that I'm right on Wolfram and Alpha real quick.
Have you used up your 2 free daily?
No, I haven't. But I'm also not looking for the steps worked out. Well, I'm not yet, unless I'm wrong, I suppose. So just to prove a point, kiddos.
What is that?
Everybody makes mistakes.
Yeah, it's just the first derivative. I'm going to derive. Now, careful. If you're doing a fraction, you got to put, I'm just trying to show you guys how to input too.
Oh, yeah.
This is like old graphing calculator before it did the nice little fraction bar. You have to put a big old parenthesis around your numerator. So we're going to have x minus 2. And then what's the denominator?
X squared minus
X plus 1.
plus 1.
Minus x plus 1?
And then that's
Squared, right?
And then
If you want to be super, super safe, you can put parentheses around that square, but you know what, PEMDAS, it's only going to square what comes directly before it, so we're probably okay. Let's double check what we got. Once again, there are other derivative calculators online. Pull out a negative 3, x squared minus 3x plus 1.
Plus minus 3, minus 3.
no, but
Okay, so they factor out.
Yeah, you pick up 3.
Okay, if I factor out. But guys, can we stop with the first derivative? Nope, let's go and get the first derivative down. That's the first step. You guys can just trust my work on this one. You have to do a quotient rule. If you guys want to check out where it got really tricky for me, I don't know if it's really tricky, but once I did the quotient rule, this would have been a horrible distribution. This would have been a horrible distribution, but I saw that there was a common x squared minus x plus 1. So even though it was to the 4th power, for a little bit from the bottom squared, I was able to factor out 1, and then I was able to cancel it. That's how I went to cubed. And CalcChat would probably do something similar if it was showing you work. It would just pull one out and cancel it without showing that. So then I had one of these left, I had this left, then I had to FOIL it all out and combine like terms, etc., etc. Our first derivative we end up with half prime of x equals negative 3. There it is. X squared minus 3x plus 1 all over x squared minus x plus 1 quantity squared. Okay, but dilemma is, what else do we need? Okay, let's go check out. Nathan was asking a second ago, can you take a second derivative directly from Wolfram? Well, let's check it. If we were to do something to the effect of... Yeah, we could just put in. Let's see if it goes straight there. Yeah, buddy. Yeah, buddy. That's pretty cool too, huh? So we could go ahead and just for sake of time, once again, kiddos, our job is not to teach you how to take derivatives today. 6x times 2x squared minus 8x plus 5 all over x squared minus x plus 1 to the power of 4.
yeah, how do you memorize that? Like the quarter of a second?
Oh, that's just the same denominator.
Oh.
So I did pull it up once to, yeah, no, my brain is not like that. I wish it was. No, I already overanalyze things way too much. I don't need it to remember everything. Anyway, coming back. Okay. How do we analyze for concavity? What's our domain? We have a domain in our pips, right? We have a denominator, true?
Yes.
That's a domain.
How do we factor something when it's not nice? Factors of 1 that make 1.
Oh, then you do the synthetic or
Yeah, but synthetic's gonna be gross.
or the other one.
Complete the square or quadratic formula. What do you want?
Complete the square.
I heard both. I heard quadratic formula first, so we'll go ahead and follow Charlotte's. Complete the square would work too. So we're doing domain. We gotta take this denominator and say this is pre-cal. That's why it's in green. Okay, let's set that equal to 0. So we have x squared minus x plus 1 equals 0. X equals negative b. That'd be positive 1 plus or minus square root of b squared minus 4ac all over 2a. How on earth am I crossing that out and just going from negative infinity to infinity? What did I see?
A negative.
It's going to be a negative under a square root. The discriminant is negative, aka the whole thing is imaginary, aka there are no zeros. There are no zeros.
I see.
That's why quadratic formula is sometimes nice. You didn't have to go through all the completing the square. If you can check b squared minus 4ac, if it's negative, stop. It's not factorable. There are no zeros. I shouldn't say not factorable. There are no zeros. They're imaginary. Pips. All right, let's take the second one. Second derivative. Top equal to 0, bottom equal to 0. Wait, can the bottom equal 0?
Let's see. Minus.
Isn't it the same bottom that we just checked?
Yeah.
So the bottom can't equal 0. No DNEs. Does that make sense? It's the same denominator from the original. So forget the bottom. But the top, ooh. Alright, so we have 6x equals 0. That's going to be at x equals 0, right? Then we have also set this guy equal to 0. 2 and 5 is 10, 10 and 1, 2 and 5, none of them make 8. So I'm going to go do quadratic formula again. We're trying to find our second pip. We already know that we have x equals 0 from the first factor, but the second, alright, x equals negative b plus or minus square root b squared minus 4ac. Ooh,
Just a question.
all over 2a. Yeah.
If you discover like the quadratic formula, can you like copyright it and then make people pay royalties every time they use it?
If you discovered it or discovered it a long time ago.
Well, I mean, probably before the copyright system, but if you found something
New.
similar or new,
You could try, but basically the quadratic formula is just a simplified completing the square. I'm not really sure there's any other new way of solving.
Oh.
Okay, I have 4 times 2 is 8, 8 times 5 is 40, 64 minus 40. Ah, bummer, guys. That's an actual number. Struggle. It's not a nice number, though. Square root of 24. 4 goes in? 6 times.
2, 6.
Square root of, yeah, so we have 8 plus or minus 2 root 6 all over 4. We can divide everything by 2, right?
Yeah.
Pull out a 2 and reduce. So we have over 2, 4 plus root 6, plus or minus. Whew! That was a party. 4 plus or minus root 6 all over 2.
And 0.
And thank you, 0.
negative.
Ooh, wait a minute. 4 minus root 6. Is it root 6 less than 4? That'd be a positive, yeah?
Wait, 4 minus 6.
Because root 6 is somewhere between root 4 and root 9, right?
Yeah, maybe like
Oh, yeah, 4 is great.
4 is greater.
Oh, but then divide by 2. Oh, but it's possible.
So we have, let's see, 4 minus 3-ish? No, less than 3. 4 minus 2-ish would be 1 point something over 2. Let's just say it's 1/2. Can someone double check the decimal real fast? I'm pretty sure 1/2 is going to be fine. -1 could be over here. That's 1/2-ish. 4 plus 2-ish would be 6-ish over 2. I'm pretty sure 1 will be fine.
It should be 0.777 is minus.
Perfect. So then 1/2 is going to be less than. What I did is I figured out it was a little more than 1/2, so I just used 1/2. This one I figured out was going to be a little more than 1. So I used 1, and then I just went 3. You can go 4, you can go 10. But then, kiddos, the name of the game is to go ahead and double check the concavity, right? This calculator's close. Hey, kiddos, if you are allowed to use your calculator, which this one is going to be decimals, maybe not. But if you are using your calculator, how could you simplify plugging in 4 different numbers to the exact same function if you are cheating and using your calculator? Which in homework, sometimes we gotta do what we gotta do.
Type in the function.
Type in the function where though? In the graph. Graph the function, right? So I can do like 6x, I'm doing it in my y1 as I speak, times 2x squared minus 8x plus 5. And then in the denominator, I use my really nifty like alpha fraction button. X squared minus x plus 1 to the power of 4. And then I'm going to the home screen. What am I going to do?
Y1.
Y1, alpha trace. Then I can do y1 of -1. Then I can go up and actually go steal the y1 again. I think it's easier. And I can do 1/2. I can go steal it. I can do 1. And I can go steal it. And so far I've got negative, positive, negative, and now I'm going to plug in what, like 3? Nathan can double check me. Ooh, it's negative again. I took the function and I plugged and chugged. Now here's where it's a little weird. Question, We can analyze for concavity, we can state the intervals. My question to you is, where are the points of inflection?
0.
Some people call them the poise, P-O-I. I call them ifs, the inflection points. I am going to have one at 0, but where else?
Also,
But what about that guy?
No, because there's no.
There's no change. There has to be a sign change. If I wanted the actual point, I go back and plug in and find my y. But to find points of inflection, we have to find the second derivative. This was to prove to you some second derivatives are nasty, some are easier. But find the pips, make a sign chart, all from the second derivative. And we end up with an inflection point at 0. Here we go, concave down to concave up. And then at 4 minus root 6, a little bit less, concave up to concave down, and that's it. It's going to be a horizontal asymptote. There were no more. There were only 2, and we found both of them right there. Boop, boop. Okay, there was another example for us, but you guys can tell some of these, oh, that derivative wouldn't have been bad. We should have done him. Oh, well. Last idea. Last idea. You go and make it big. If you want, you can grab out your phone and take a quick picture of it. If you want to just wait and pay attention and copy it down tonight. Last big idea. It is a forever card.
Oh my. The speed.
It's exactly like the last section. Increasing, decreasing had a forever card, but also relative extrema from the first derivative had a forever card. Same thing here. Concavity has a forever card. Well, actually, inflection point has a forever card. So does how to find relative extrema from the second derivative. Forever number 27. What I want you guys to still understand is relative extrema only can occur at critical numbers. That hasn't changed. Relative extrema can only occur at critical numbers. But you don't have to have a first derivative sign chart to always, well, that's not the only way to find every critical number. And here's the reason why. Once you find your critical numbers, which are still f prime pitchfork, where the original function exists, once you find critical numbers, still the first derivative sign chart, you can actually take the c's and you can plug in. And if f double prime of a critical number is positive or greater than 0, I know f is concave up. And if there is a critical number of a concave up graph, if there is a critical number on a concave up graph, that point has to be a relative min. If f double prime at the critical number is negative, then f will be concave down. And if there is a critical number on a concave down graph, it's going to occur at a relative max. And if the second derivative equals 0, all bets are off. We don't know. We have to, the graph has to have concavity in order for us to know from the second derivative whether a critical number is a relative min or a relative max. But the long story short is, you still find the discontinuities and the critical numbers, but you don't do a sign chart. You plug into f double prime and you test the concavity. Kiddos, that's the last idea in homework. Have it down. That's the last idea in homework. Have it down. Check out examples in the book. But to find a relative min or a relative max, you guys need to pack up and get out of here. Use the second derivative, find the critical numbers, plug into f double prime and say, what's the concavity? And then look at the concavity and say, oh, it's a min. If it's concave up, ooh, it's a max. If it's concave up. Bye, guys. Because no concavity, all bets are off. You only can say min, concave up, or
If
At one point it's like that, but the graph is like that. I don't know what's going on before or after I do the sign chart. Because if you have concave up, I know decreasing before, increasing after. So I can cheat and say relative min. If I know concave down, I know increasing, decreasing. But if zero, I don't know before or after. It might be like this, no code at all. It could just be something like this, where it's in between. It could be an in between, so there's then no min or max.
Yeah.
Go fast.
Outlet. No, outlet. They're like an
Oh, you mean battery?
Yeah.
You can plug it in. You can put it on the whiteboard, check.